Welcome back to ECE 441A, 541A. Few announcements. Maybe the big one is you do not need to show up for class on Friday. It's homecoming weekend, and because of that, I will not be in office hours on Friday either. But if you need to see me, let me know, and we'll set something up. Probably not on Friday. Yes.
Are you going to be doing a video or anything?
I haven't decided. I'm afraid with all of these Veterans Day and Engineer's Breakfast, I may have to start making up some lectures. So stay tuned, and I'll send you an email if I want you to watch something or if I provide you additional information. So keep a watch out for that, and I don't know whether I will do that or not, but I probably will at some point. I sort of want to be having an audience when we're doing the root locus rules, so I may hold off on those canned lectures or the recorded stuff. That's what I'm thinking right now. So let's see how far we get today, but stay tuned. And lab number 2 is due on Monday, and apparently there may be a big rush to try to get into the lab from what I'm gathering after this morning's discussion before class. But we'll see. Hopefully you can make that. Don't get too worked up if there's a rush on lab times and you can't get a lab time. Today what I want to do goal-wise for class is to start with an example of how do we convert a generic characteristic polynomial into the standard root locus form, and maybe what the possible root locus patterns might be for that particular example. And I'm saying possible because it really depends on the particular values or locations of your poles and zeros as to what the structure of your root locus is going to look like. Then we will look at 2 conditions that influence all of the root locus rules. And those are a magnitude condition and a phase condition. So if you get nothing else out of today, just be thinking, oh, the root locus is all coming about because of -1. It's really a phase of 180 or -180 and a magnitude of 1. That really determines all of these rules that I will be listing quite routinely in the next few classes. You don't have to memorize these right now, but we need to get used to thinking about this process. And sometimes these rules do not apply. Depending on the kinds of poles and zeros that you start with, some of these particular rules may not actually come into play when you're sketching your root locus. But these are sort of the 6 that I have identified, and I want you to just get comfortable with sort of having those descriptions. If I say, oh, what are the starting and ending points of our root locus, you know what I may be referring to. When I say, what are the segments on the real axis that belong or live on the root locus? We're going to essentially take our real axis and treat it like a loaf of French bread and start chopping it up. And we're going to put some of those pieces on the root locus and some will not be. But that's one analogy that maybe people can sort of visualize, is this long tube of bread. Maybe I shouldn't call it a tube because that will get you confused with our settling time. We also have asymptotic behavior. Yeah, I know. I mentioned tube and I immediately thought of the 2% settling time, and apparently you guys do too, which is good. But the third rule is asymptotic behavior. We have lines that are asymptotes that our root locus will approach, and that depends on the pole zero excess. How many more poles do we have than zeros in terms of defining those angles? We will could have breakaway and reentry points on the real axis. We've seen roots coming together, then they break away. Well, they also can reenter on the real axis, and then they depart along the real axis. We'll find how we determine those breakaway and reentry points or locations. We might have a root locus that actually crosses the imaginary axis. And it might be nice to be able to determine where does the root locus cross the imaginary axis. Obviously, if branches go into the imaginary or into the right half plane, at that value of k, we're now becoming unstable. You'll have a homework problem where they go unstable and then you crank up the gain k and it comes back. So that's called conditionally stable, and it depends on how you tweak your adjusting knob on k. For some values it might be unstable, for other values it might be stable, then it might go unstable again. So it's very fun with adjusting this knob. The last one that I have identified concerns angles of arrival and departure, and this is getting a little bit detailed, but it's sort of nice to keep in mind. If you have complex poles or zeros, how are you departing from those complex poles, or how are you arriving? So now think of you're approaching a zero, and at what angle are you approaching that zero? Those are the angles of arrival, and how are you leaving the poles? How are you departing? What's that departing angle? And these angles are all defined relative to a horizontal positive in the right direction segment. And so we're referencing that sort of going off to the right on a horizontal line, and those will be our angles defined relative to that particular defining line. Let's look at an example before we get into root locus construction of how to find or how to create this standard root locus structure from a generic characteristic polynomial equation. And here, how are the closed loop poles affected by adjusting a gain k from 0 all the way up to k going up to infinity. And now let me sketch the block diagram, and this is not a conventional or traditional structure. We have a set of dynamics there that has two real poles. We then feed that through an integrator, and that produces our output y. On the far left is our reference input, but then we actually are going to measure that output y and compare it or add it in actually to the unintegrated signal coming out of that first block, and then feed that combination back to produce this difference of our reference input and this linear combination of signals coming in from the right. And so this is not the traditional block diagram, and we wouldn't expect to see this typical k in the denominator of 1 plus k g of s h of s that we might typically think is going to appear or be there. And what we want to do now is find the closed loop transfer function, determine how k enters into the denominator of that closed loop transfer function, and then transform that characteristic equation or that denominator expression into the standard root locus form. That's the strategy that we want to apply now, meaning we're interested in the transfer function between the reference input r and the output y. So I'll call that our closed loop transfer function. And in fact, let me just write that down. That's 1 over s times s plus 1 times s plus 2 plus ks plus 1. And that was by inspection. No, not really. But I'm just seeing how alert everyone is on a Wednesday morning. But how would we maybe find this closed loop transfer function? You should have a idea as to how you might do that. What's one way that you could potentially find this closed loop transfer function from this block diagram? Mason's gain. That's what I was expecting you would answer. Now, how many paths do we have between the reference input and the output Y? I see 1. Is there any more? No. And now, how many loops do we have? So I'm going to try to return your exams at the end part of class, and you'll realize that maybe sometimes paths and loops get a little confusing with Mason's gain. But you cannot go against the arrows in finding these loops. And some people were actually sort of creating more loops than we needed on some of the exam problems. But in this case, if I go around here, I could do that one. Yes. And, I could do this one, right? And I don't have any other loops. So I have 2 loops and 1 path. And I can find my denominator. How many cofactors do I have? I just have 1 because I only have 1 path. So let's write those down as far as what we have for this particular case. The path was straight across, and that's just this product of those 2 in the top branch of this block diagram. Or it's now 1 over S times S plus 1 times S plus 2. In terms of my loops, the blue loop is really very similar to the first path, except I have a negative sign introduced because it's now circling back around. But there's no gain in that feedback path that I'm pursuing in that first loop. So actually in my notes I called that loop 2, but it won't matter. So I'll say loop 1 is now minus 1 over S plus 1, S plus 2. Are we okay with that? And then loop 2 does pick up a K. And we don't want to miss the minus sign, but it does not have that pure integrator as a part of it. And we then have for loop 2 a minus K over S plus 1, S plus 2. Is that okay? Now we can form our determinant. And people were they were sort of having trouble with this and the cofactors. In terms of these loops, are they touching? Yes, because you see common segments of blue and green. So these are touching loops. We don't have any product of pairs. Since we only have 2, we would only have 1 pair, and it touches, so we're not going to have L1 times L2. We just have 1 minus the sum of those loops. And what about our cofactor? If I remove that yellow band, does that disconnect any of the loops? Yeah, it disconnects them all. So I just have a cofactor of 1. There's my cofactor. And now I can show you maybe a little bit more believably where that transfer function came from. That's just this piece. It's P1, which was the first path. 1 over s, s plus 1, s plus 2, times 1, all over the determinant, which is 1 plus 1 over s, s plus 1, s plus 2, plus k over s plus 1, s plus 2. Does that look okay? And now if I put everything over a common denominator, that 1 is going to be a ratio of this s times s plus 1 times s plus 2, and the k will be scaled by s. And then I can cancel the denominators in the numerator and denominator to end up with the following. 1 over, the numerator is clean, and now I had an s times an s plus 1 times an s plus 2. That came in from the 1, where it was the ratio of that expression, plus 1 plus k times s. And that should be consistent with the transfer function that I just wrote down and jokingly said by inspection. It wasn't by inspection, okay? But you can see that this is not the traditional block diagram that we're interested in finding, but what is our using? What's our characteristic equation? Or what we are now referring to as the characteristic equation. That's just our denominator in our closed loop transfer function, which in this case is this s times s plus 1 times s plus 2 plus ks plus 1. And how do I put it into the standard form? I want a 1 plus k n of s d of s equaling 0. I'm going to set delta of s equal to 0, so really I'm looking for that right-hand side to be converted into something that looks like a 1 plus k times a ratio of polynomials. And I can do that by identifying all of the terms that contain the k, which is only 1, and dividing by everything else. So that I now have 1 plus k times s over s times s plus 1, s plus 2 plus 1. And that's going to equal 0. Right on cue. Pardon? No, class is not over. That was not the cue that I'm looking for. That's just a cue to indicate that, wow, we really reached the expression that we wanted. Is it clear where that came from the characteristic equation? We're just dividing out everything that doesn't have a k associated with it. Now what do we do? Well, we now need to identify the zeros of n of s, or the roots of n of s, which we will call our open loop zeros, and the roots of d of s, which we will call our open loop poles, which really aren't connected in this case to any kind of the open loop poles or zeros in this representation. So now what we want to do is we want to say what are the open loop, and that's in quotes because it's really just pertaining to this standard form that we're referring to them as open loop zeros. What's my little n of s? And so now I'm looking at values of s that cause that to vanish. That's a very tough one. That one you can do by inspection, right? Our 0 open loop is at 0. And now we need to find our open loop poles. And that's this d of s, that's s, s plus 1, s plus 2 plus 1. And if we didn't have that plus 1, it'd be easy. It'd already be factored. But we have that additional constant hanging off the end, so that we now have s times s squared plus 3s plus 2 plus 1 equaling 0. So we're now trying to find the values of s that cause this to vanish, or to equal the right-hand side. And this now says we have s cubed plus 3s squared plus 2s plus 1 equaling 0. And this is now our, let's say, well, that's what we were calling our d of s. So let me just call it d of s. And what's going to happen here? How many open loop poles do you have? 3. And where are they? It may not be easy to see, but we could sketch this if we wanted to as a function of s, and maybe it does something like this. What does this graph of d of s tell us in terms of the roots of that expression? How many real roots do we have? So this is maybe confusing. Don't get too locked up on the s-plane. This is just d of s relative to or plotted against s. We're just trying to find values of s that cause d of s to vanish. I see one that's real. Yes, if there were 3 real roots, this cubic would cross the horizontal axis 3 different times. What's going on? I have one root from a cubic. The others are complex, aren't they? We have 2 complex, and they will appear in conjugate pairs because we have real coefficients. But this sketch, if this was actually and you could do this with your calculator, you could plot as a function of s this curve and see, oh, I have one real root. You could now find that, and you could then identify your quadratic and do the quadratic formula to obtain your complex roots. If you do that, in this case, the roots of that d of s are now at minus 2.3, and the others are complex, and they're at minus 0.34 plus and minus j 0.56. And these are what we are calling the open loop poles, or the roots of d of s in our standard root locus form. Pardon? You could use your calculator to find the roots. If you had a fancier calculator, you could do complex zeros or C zeros, and it will find those 3 values. If you don't, then maybe you sketch this and you go, oh, I have one real, which you would expect. If you have 3 roots, you can't have a pair of complex dividing 3, only one pair of complex. And so that's what we have, and we can now plot those in an s-plane. We had a 0 at the origin. We had a pole at minus 2.3, and we had another set of poles at minus 0.34 plus and minus j 0.56. So let me say those are right about there. And those are supposed to be mirror images across the real axis. Those are complex conjugate roots. What we want to do now is sketch the pattern of closed loop poles as we adjust k from 0 to infinity. And we haven't talked about the rules, so this is now going to all appear like magic at this point, but I want you to think about what you have. How many open loop poles do you have? I'll give you some questions that should have easy answers. How many open loop poles do you have? 3. How many closed loop poles are you going to have? The same number, 3. Okay? How many zeros do you have? You have 1. What's the pole 0 excess? How many more poles do you have than zeros? 2. You have 3 minus 1. This is really tough math. Okay? So those are immediate concepts or quantities that you want to sort of keep track of. Now that we know that we have, and we will learn these rules, but one of those rules is which segments of the real line are on the root locus. And now all we have to really worry about in that rule is how do we divide up our loaf of French bread. And by doing that, we're really saying where are our poles and zeros on the real line. And if we have them, those will form a cut in our bread. So if we think about that on this real line, how many pieces of French bread do we have? How many times have we cut our loaf? We cut it twice, so how many segments do we have? 3. Is that clear? We have a right end, we have a left end, and we have a middle piece. And if you're lucky, you'll get one of the end pieces, you'll get more bread, right? But that's not what we're interested in right now. I have to wait a little bit longer before I can worry about eating. Okay, so we have a piece from minus 2.3 to minus infinity, a piece from 0 to minus 2.3, and a piece from 0 to plus infinity. Those are our segments, and we want to know which part of the real line or which of those segments belongs to the root locus. We will learn that in this case, it's actually this piece. We start at poles and we move to the zeros, so we will have a branch of our root locus between minus 2.3 and 0. Now, what was our pole 0 excess? 2. So we will learn that the asymptotes are determined by taking 180 degrees and dividing by that pole 0 excess. So our asymptotes are at 90 degrees and minus 90 degrees, which means that 2 of these branches are going to, and we'll learn about the angle of departure. Maybe these depart this way and they approach an asymptote. Maybe our asymptote, there's the one at 90 and here's the one at minus 90, and now this one goes as the mirror image, and they just approach those asymptotes. That's one possible pattern for the root locus. And what does this tell you about K? Is there a limit on K that you can adjust that knob before you become unstable? Yes, there is a K beyond which you're going to be in the right half plane, and you probably don't want to adjust your gain K any larger than that. Now, what's another possible pattern? But it all depends on the relative spacings of these poles and zeros. Let me just quickly... This hasn't changed, but here's something that could really be fun. These could maybe depart, and this is why the angle of departure is interesting. Maybe the angle of departure here is like 160 degrees, so it goes there. And in the earlier case, the angle of departure, let's say, is 40 degrees. Do you see how I'm measuring the angles? The angles are all relative to this horizontal line. And maybe this one's 190 degrees. I was saying if it was 170, I'm thinking it bumped up a little bit before it came back down. But we still have a pole 0 excess of 2, so we have asymptotes at plus and minus 90. So here, follow along on this magic school bus ride. I'm going to start on the complex root in the second quadrant, and I'm going to follow that path. Then I'm going to approach the real line, and then this one actually is going to go off to the origin. The one from below is going to go off, and he has to go a different direction. He goes left. And so the request was to make it different colors, and I'm running out of colors, but these two then meet, and they can't stay together. They just don't get along, so they separate, they break away, and they now approach asymptotes. So in a 30,000 foot view of this, if both of those asymptotes were at the same location, these pictures would look similar. But near the origin, they may look quite a bit different. These actually came and approached the real line and then went away. These never went to the real line to begin with. Question? Pardon?
If I understand, the red line shows the possibility of groups that we can have.
So the red line in both of these graphs or patterns, root locus, determine the possible closed loop poles in this system as we adjust k from 0 to infinity. And we'll have to figure out which of those patterns it is. And by these rules, we'll be able to determine that. But I'm just now giving you right now some open questions or ideas about what the pattern might look like. So those red lines are the closed loop poles in this particular system. So now the k, so if k is 0, where am I? If k is equal to 0, where am I in this top root locus pattern? I'm at the open loop poles, open loop in quotes, so I'm at these complex at minus whatever it was, minus 0.3 something, 0.34 plus and minus j, 0.56, and minus 2.3. As I increase the gain k, if I get k a little bit bigger, let's say 1, well, let's not go that big, let's say 0.5. Now this pole at minus 2.3 may have migrated to minus 1.3. The two complex have left those two poles, and now they're moving. Maybe they're already into the right half plane with a gain of 1/2. And we would have to determine where did it cross the imaginary axis, and at what gain did it cross that imaginary axis. So if the gain is 0, if k is 0 here, then in this case it's a little bit different, but in this standard form, if k is 0, then we would be locked on those particular poles. So let's move on right now, because you've raised a good point, and we'll have to come back to that, but that's because the point being made, I think, is all hinging on that non-traditional pattern of the block diagram. So let's look at some of these rules so that we can understand which of these two patterns we might have in the complex S-plane, okay, of those two possibilities. So the root locus is now going to involve little n, and these are paths or branches. And so if I go back here, how many branches do I have in this picture? Maybe I will try to do this in a highlighted color. So let's say that this branch is right there. There's one branch. Another branch is this one. And then where it goes, let's just say that it went down. And then a third branch would be that. Now, it doesn't matter whether this one on the left starts left and then goes up or goes down. We're going to have those two going in combination. But do you see the three different colors and the three different branches? And how many poles did we start with? 3. How many did we end up with? 3. We have 3 branches. And how we adjust the gain is going to influence where we end up on those three branches. So,
This is random.
so what I've drawn right now is somewhat arbitrary, but in patterns, it's either this pattern or that pattern. Here, it's maybe easier to think about the branches. Here's one branch. Here's another branch. And then we have a third branch. Is it clear the paths that we have? They start on the open loop poles and they leave and approach zeros. Some of those zeros are finite zeros and some are at infinity. And those infinite zeros are determined by the asymptotes, where those asymptotes take us. So we have n paths or branches in the S-plane. Showing how the closed loop poles actually change or move as our adjustable parameter. In this case, it's k. In the homework, you might actually have an adjustable parameter that's a, but here the parameter is k, is varied from a 0 to a very large value, which we just say is infinity. And as a reminder, our basic block diagram, let me draw this in two different options. And the options are going to be determined by the sign of the feedback path. We have a gain k, we have possibly a controller, G sub C, and a plant, we'll call that G. And a lot of times, let me call that G bar so that I can now call this whole combination our forward path G. Is that okay? So the combination of controller and plant, I'm going to probably just all lump into a G in this discussion. That now yields an output Y. And we have the possibility of some dynamics in the feedback path. And those will then get compared with the reference input. But what I want to do here is, let's say that this is coming in with a positive sign, but maybe we have a negative sign, or depending on who builds this, maybe they've put in positive feedback. So this is then going to be positive feedback. And this one will be negative feedback, and that's the one that we will typically just assume that we have. But depending on whether we have a negative feedback or positive feedback, that will influence the sign in our denominator expression, whether it will be a plus or a minus. So our closed loop transfer function you now know from your cheer is this ratio of y to r, and that's now k, g sub c of s, g of s, that was the g, over, and our cheer was based on negative feedback, and so that gave us this plus sign. If it was positive feedback, it would be a minus sign in that denominator expression. K, G sub C, G, H. If we had positive feedback, that would be a minus sign, and I'm making a big deal about that because we're eventually going to be setting that denominator equal to 0 and then trying to find the roots of that as we adjust k. Question? Oh, thank you. Those are the g-bar. Thank you. So that's supposed to be a g-bar. Was that your question? So the combination of g sub c and g-bar produce the g, and the positive sign in the denominator is associated with negative feedback. And if we're interested now in the roots of our denominator, or those are now our characteristic equation, then we have 1 k g sub c g h equaling 0, and what's in between that is either a plus sign or a minus sign, depending on whether we have positive feedback or negative feedback. And you can derive that from the block diagram algebra. You know where those signs are arising from or how they're coming into play. And we typically have negative feedback, so we use the blue and we have 1 plus k g sub c g bar h. We are going to, in this class, actually focus on the negative feedback, because if we did the positive feedback, we would have 2 sets of rules. There's no reason to be that confusing in discussing the root locus. Let's just focus on always having negative feedback, and then we can establish these rules. But bear in mind, if somebody now says, oh, your phase angle condition is different, well, then they're probably talking maybe about positive feedback. But we will deal with negative feedback and focus our attention that way. And if we do that, then we end up with 1 plus k g of s h of s. Now I've combined g sub c and g bar into 1. And what does this now give us? If we solve that equation, I now have k g of s h of s equaling minus 1. Haven't done any fancy math there, but now what I want to realize is that minus 1 can be written as a magnitude of 1 at an angle either of plus 180 or minus 180. I like to just refer to it as minus 180 in case it corresponds to like a delay. So that we're now interested in this point minus 1, and we can get there via this distance of 1 and either going 180 degrees that way or minus 180 degrees that way. And the 2 conditions that we have then is that if we looked at the magnitude of the left-hand side, that must equal 1. So this k g of s h of s has a magnitude of 1, and what's the phase of that expression? Minus 180 degrees. Those are our 2 conditions that determine or impact all of our root locus design rules. And that's what we will start with the next time we meet in person or virtually, with these 2 conditions deriving all of the rules that we talked about at the first of class, those 6 rules. But they all hinge on this very simple expression. We take the magnitude, it equals 1. We look at the phase, it's minus 180. And we'll pick up there the next time.